Hello, let us do some formula based revision of the electrostatics. And in this particular video, I have not covered all the formulas. And one disclaimer which I would like to make before you go on to watch the whole video is that this video is beneficial for the people who are planning to give JAM in the coming month and GATE. So the reason I say this because we all know that JAM is not more conceptual bit. It's more like a knowledge based exam. So if you are planning to give JAM in the coming month, then this would be a really nice video for you to go through. And on the other part, I would always suggest that do go through the derivation, the rigorous derivations given in the standard textbooks. And yeah, that's the only disclaimer which I wish to present before we move on. Okay, so the very first topic that we have is the charge and charge density. So in the video, I will just go on with the formula and just explain stuff. So by charge, so if you have any body having some charge q, you must always remember that the charge is quantized in the system. So q is equal to ne, and this n is belonging to some integer natural number, and you won't find charges in fraction, at least at the JAM level, and I have not heard of any fractional charges till now. Also, the one point that you must remember is in isolated system, it's conserved. Okay, so if you are in the exams, in the competitive exams, the questions we are asked are mostly about the isolated systems. We are given some sort of a sphere, a cylinder or something, and we are asked to calculate some sort of field and something, whatever. So in these, all the charges around the object, unless otherwise mentioned, if they are losing or gaining some sort of charges from external place, they are conserved. All right, now we have charge density. This is similar to what we have in the mass systems. So for mass system, we have something known as mass density. Similarly, we have something called as charge density. So over here in the charge density, we have some three different formats. Okay, one is linear, other is surface, and the last one is volume. Okay, so with linear we have lambda equals to dq by dl. So in this we have some one-dimensional object. Okay, and in the very small dl element we have charge dq. All right, so now for surface we have sigma equals to dq by dA. So over here we have some sort of a 2D element or a 2D structure where we have this small element dA. Please pardon me, it's dA over here, and the area and the charge element is dq. Like, it means that in that particular D element we have some dq charges. All right, now finally rho equals to dq by dv. So let's say we have this 3D structure, and in this element, small element dv, we have dq charge. I hope this is clear, and these are the very basics which are like usually taught at what do you say, around 12th standard when you have the electromagnetic theory some chapters. Okay, and one important point to note is, let me change my color for for uniform body, this dq by du equals to constant. So what this du can be anything like length, area, or volume. This can be anything, and it will be a constant quantity. All right. Now the next topic that we will deal with is a resultant of vectors. Okay. Now let's say we have two vectors a, b with angle theta between them, and the resultant will be using the vector addition. Then the resultant that we have is a square plus b square plus 2ab cos theta. Alright. Now our resultant will be somewhere between this a and b. Sure. I hope you are following this. Then I have case 1 when my a vector is greater than b, and my case 2 when my b vector is greater than a. Let me redraw the structures. A, B, A, B. Sure. Now my resultant will be more towards the side of A, and over here my resultant will be more towards the side of B. Okay, so this is something you can also understand intuitively how this comes along. That if I pull, if you can imagine this as a tug of war, and if you pull equally from both sides, the center will be at the same position. But if you give more force on some side, then the center of that rope will tend to go on that side over where you have more force. So similarly, we can understand this through an analogy of tug of war. And the important case over here is, this is the special case, and I really want you to consider, or rather say remember this, because this is gonna help in your EMT very much. So this is the special case that we have. So in special case, I have A equals to B. Okay, now I have two vectors A and A with angle theta between them, and my resultant will now lie exactly on the line bisecting these two. Okay, this can also be written as A. So my resultant will be like lying between the two. This is theta by 2 and this is theta by 2, and the value of this resultant over here we can calculate, and that would be 2a cos theta by 2. I want you to remember this throughout the EMT course, or whatever you are taking, let it be at the BSc or MSc level. And the other important thing as a mathematical tool, which is always helpful in many of the coming branches of physics. So the binomial expansion is something one must not forget, because it always helps you to get back to do some sort of approximation. So the binomial expansion of 1 plus x to the power n will be 1 plus nx plus n minus 1 upon 2 factorial x square plus. So it will go on, or basically we can write this as I equals to 0 to infinity n, right, let me form a series of this. Yeah, so this will be the series NCI x to the power I, and in usual textbooks you will find this as NCR x to the power R. So let me just go with the standard notations. Now we are coming to the major part, that is the Coulomb's law and its different forms. Okay, so we usually have a very vague idea of what Coulomb law is, and we just take it for granted that it's just k q1 q2 by r square. But this will usually not help while you are solving the problems. So we must understand what goes behind the Coulomb's law. So this is the r bar, and this is my origin, q1 charge, q2 charge, and I have r1, r2. Okay, so Coulomb's law actually comes from, like, you can understand this figure and like go for the Coulomb's law. And the other form, which is the important form while you go through questions, that is the vector form. And that is F21, that is the force applied on charge 2 with respect to charge 1. Okay, and that will be K q1 q2 r2 bar minus r1 bar upon r2 bar minus r1 bar whole cube. One thing which I wish to bring to your attention is the vector notations of this charge, of this distance r2 bar and r1 bar are vectors, and they need to be added vectorially. Alright, so this is something we usually don't focus on. And moving on to the next topic, that is the general method to find force between, then we have three cases, that is point body and body. Okay, so for point we have already seen how to calculate this, and for first I will go for the case 2. So let's say I have a point and then I have a body over here. Okay, now I will take a element area on this body and calculate the electric field with respect to this particular box or the element. So what I mean to say is I will divide the whole body into the boxes, and then for individual boxes I will calculate the E and add it. So at this moment it seems very difficult, but the questions that are being asked in the question are having some sort of a geometrical importance. So for it will usually ask you for some sphere or some cylinder. So you understand that it will be easy for you to integrate and get the electric field. Okay, and for the last case, that is body. So let's say we have one body over here and another body over here. In this case we will take element on this and this other body, then we will calculate the electric field between two, and then for this particular element on body 1 we will calculate the net field of the, because of all the charges on body 2, and then we will integrate the two bodies, and that's the way it will roll out. Okay, now the asymptotic variations. So let's move ahead with this topic. So for asymptotic variation, I will choose two charges. Okay, my charge 1 and charge 2. Let me describe that by Q1 and Q2. Okay, and with respect to some third Q0 test charge, okay, now I will see what is the variation of force when I see this system of charge from a large distance. Okay, so in this we have case 1. So the case 1 is summation of Q is not equal to 0. So let's say my Q1 and Q2 both are positive, then my force will be proportional to 1 by r square. Okay, now case 2, summation of Q is equal to 0 and summation of dipole moment is not equal to 0. So let's say my Q1 and Q2 are, let's say my Q1 is positive and Q2 is negative. So I have my dipole on this side. It's not equal to 0, right? Then at point Q0, my force will be proportional to 1 by RQ. Case 3, it would be summation Q one second, summation Q equals to 0 and summation P equals to 0. Let me give an example. If I have minus Q plus Q plus Q and minus Q as a system of 4 charges, then my summation Q and the two dipole moments that it's forming will also be 0. Alright, so in this case my force will be proportional to 1 by r to the power 4. So these are the 3 relations which you can prove taking the examples. You can get the exact formula and see if they are proportional to these inverse distances. But in exams sometimes we don't get enough time to go through all of this, and it's better to remember these things for exam perspective, but in general you must go through the whole rigorous derivation. Now equal charges in regular polygon. So you will be very familiar with this kind of examples. Okay, this is, let's say I have a triangle with all vertex having charges as Q, and now what is the force at center? That will be 0, and that's true for any general regular polygon. Okay, so let's say I have a polygon. Let me draw some bigger polygon, a regular polygon, and all the corners are having same charges. Then at my center the charge will be 0, the force will be 0 at center. Alright, let's move to the next concept, the electric field definition. So that's quite simple. In a very naive way I can define my electric field as F by Q0. Okay, and for electric field, if I have a charge positive Q, then my electric field lines will be going out of that source charge. So I call this Q as source charge because it's providing electric field to the environment. And now I have, say, minus Q, and then my electric field lines will be converging to this minus Q, and that's why we call this as a sink point. So this source and sink, you can also have an analogy with the thermodynamics. If you can remember the Carnot engine, uh, there you have a source and a sink. It's just a terminal analogy that I am giving you. All right. Now, yeah, there is a remark about electric field that, let's say, if you have a symmetric object, all right, then your electric field will be along, like electric field is always along that the symmetric line that we have. Okay, and a point, this is something text, you must remember the point in space which is not at infinity, where electric field is equal to 0, is known as neutral point, and that is a part of our next discussion coming up. All right, so over here we have, like, the first we'll go through what is the general method to find a neutral point, and then we'll go along how it will map, like how the electric field will be along the neutral point. All right. So a very general way to find a neutral point is if direction of E reverses at some point where no charge, like in the space we have electric field, and it will be varying with respect to how the, like, the object is. So if, like, there are many objects, we are considering a multi-object system, and each one of them is having the charge or something on it, then then at some point in space where there is no charge, that particular point have no charge on it, and if we are moving from one body to other body, if the arrow of electric field line is changing abruptly at that particular point, like with a 180-degree change, then that particular point is known as the neutral point. Okay, so with the example, I think you will understand what exactly I'm trying to convey you over here. Then that will be neutral point. Sorry. Now let us take a very simple example which will be very easy for you to follow at the point. So let's say I have two positive charges, two equal positive charges. Okay, this is just my graphical plane. So these are the 2 point charges in my plane. Okay, now imagine I am standing at point Q and I am moving away from point Q. So I will see that with respect, as soon as I move from point Q towards left, I will see that electric field lines are towards the left, even at infinity. Okay, similarly from point Q on the right side, if I move towards the right side on if infinity, then I see my electric field is also on the right side. All right, but when I'm at point charge 1. So let me call this as 1. This is at 2 when I'm at my point charge 1 and I start to move towards right. So since I'm near to point charge 1, I will see that the effect of charge 1 is more, and that's why my net electric field will be towards right. Similarly for point charge 2, so there will be a point between these two arrows where the arrows will exchange. Alright, so this is my neutral point. I hope you get the clear idea of what exactly is the neutral point. And now coming to the how we will graph the electric field. The point is, if you try to calculate the electric field, it will go something like this. Oh, and one thing always remember, when you go to infinity, your electric field reduces to 0. So this is something you should not forget. Okay, I think I have given you an example. So one more statement which I will give you. So just accept this statement as I am not in a position, like this particular video is only for the revision purpose with the formula base. I'm just giving you the statement which you can remember, and in case if asked in exam, you can like recall this question and solve the problem. If there are equal charges on vertices of n-sided regular polygon, then there will be n+1 neutral points. So just remember this thing, and if you want you can try to do that for, let's say, four chart system, a square, a rectangle, something. So these are the two important things you must remember. Now the proportional relation. So this comes handy when you are given the questions that have too many of diagrams, right? Now let me use a dark ink. Number of field lines for a charge. Okay, this is 1 point, and magnitude of charge. So these are proportional. Okay, so let's say I have a charge 2q and charge q. So I will be having more field lines towards charge 2q. Oh, sorry. One thing to remember, the field lines never cross each other. Okay. So you can see the density of lines around 2q is more than the density of lines around q. Alright, and now the equation of lines, and this is a good formula to remember, that Ey by Ex equals to dy by dx. So if you have if you are able to find the y component of the electric field and the x component of the electric field, you just go on to take the ratio and equate it to dy by dx in the Cartesian plane. And for ER by E theta equals to dr by d theta, this is for Cartesian plane. And this one is for spherical polar plane. Alright, now we'll come towards the extended objects and try to find the electric field at a certain point. Alright, now as I've told you, so this particular slide gives us the arc. So this arc is a positive charge arc in space, somewhere in the space, okay, with the radius as r, and the alpha made by the two extremes of the arc is like alpha is the angle made by the two extremes. Okay, now at the center you will find electric field in this direction. Let me call this direction as minus z cap. Okay, this is just for convention, and I hope you won't just blindly follow this minus z cap. Okay, this is just the convention I'm using over here. So the formula of my electric field will be E equals to 2k lambda by r sine alpha by 2. Okay, so just learn this formula. Like I must say, it's hardly taking 15 minutes to like do this on your own independently, like going through no reference. It's easy actually, but it's up to you. If you wish to do like that, would be better for you in the exam to understand. Now I have a similar system. Now if I increase my alpha to a some normals or standard value that we use in our day-to-day lives as one second. As 180 degree. Alright, I will just put value of alpha equals to 180 degree in the formula. So I'll just put the value and I will get my E as 2k lambda by r minus z cap. Okay, so my electric field will be on this side. I don't know why. Alright, now the last case for the wire is the quarter. Okay, so let's say I have a quarter of line charge. Alright, so this is my 90 degree of line charge, and then my electric field will be on the bisecting line, that is at 45 degree. Okay, and I will just put the value of alpha equals to 90 degree in the formula, and I get my E as root 2k lambda by r. So that's my electric field, and I can then like divide it into components along minus z cap and minus x or y cap, whatever is the Cartesian or whatever is the space that wire is lying in. Alright, now we'll move to the case of electric field due to long wire. 1 second. Okay, so in this case, I have this as a long wire, one-sided infinite long wire, and this is the length D. Okay, and the charge density on the wire is lambda. So my electric field will be along 45 degree. Okay, and the value of my electric field will be minus k lambda by d I cap plus k lambda by d j cap, or if I want to take the modulus, then it would be root 2 k lambda by d. But I would ask you to remember the vector formula. So it's just inclined by angle 45 degree on the other side of the line charge. Alright, now we'll see a special case of this wire where I have an infinite wire, minus infinity to plus infinity, and somewhere in the middle I have to find the electric field, and the charge density is lambda. Alright, in this case what we can do is divide this infinite wire into two pieces of half infinite wires. Okay, and from here I will have an electric field on this side, and from this part I will have an electric field on this side. So I will have two electric fields at a point with some angle, that is pi by 2. So I have this as E and E. Now I will go back to the first page wherein we learned this. If I have two vectors with their resultant will be on their bisector with angle theta by 2. Okay, now I'll apply that particular thing over here, and I will get my E as 2E cos theta by 2, and I will put the value of my E, that is root 2 k lambda by d, and my theta is pi by 2. Okay, then I will come to a value of 2 k lambda by d. So my E becomes 2 k lambda by d. So this is something the candidate must remember, and it's often asked. This case is a special one, and it's often asked. So don't forget to remember this. Okay, now to the last part wherein we have to calculate electric field due to ring at the axial point. So in many standard textbooks you will find the derivation of this particular case, but I won't go into the derivation because, as I told, that this particular video is solely for the formula based revision. So my electric field, I have this ring with total charge Q, radius R, and distance of point where I have to calculate the electric field as X. So my electric field will be along X cap, let's say, and the value of electric field will be KQX upon R square plus X square 3 by 2 along X cap. One thing if I have not mentioned, this is important. Whenever you write electric field, it's a vector quantity. I, even as a MSc student, I do miss it sometimes while writing electric field, but believe me, it's really important to write the vector component. Alright, so this formula is something the student must by heart, and there are cases. So one of the case is what will be the electric field close to R and away from, like when my particle is over here, or when my particle is at infinity, what will be the electric field. So I think you can just go on to expand it with the Taylor expansion and go ahead. Okay, now let me redraw this system. All right, so this is my X, this is my ring, and my Y is the electric field graph, and this ring is actually not here, just for the graphical purpose. Now my graph of E will be something like this, and it will reach maximum at certain point on X, and that point is R by root 2. It will happen similarly on the other side. I'm just considering on the positive x-axis that Ri root 2, there will be E max. Alright, now this is the last example that we have for the day, and the example is I have a disk with a sigma as my surface charge density. This is a constant surface charge density. Alright, now I have to find the electric field at point Z, and one thing we can say for sure, that electric field will be along Z cap. Okay, because this is a symmetric object and the symmetric line is the Z axis. Now my electric field will be sigma by 2 epsilon 1 minus Z square plus R square along Z cap. So this is a very nice thing to remember. Again, the derivation is something you can work on from the standard textbooks. Alright, now the special case in the charged disk is when my R tends to infinity. So let's imagine this as my circular disk. It's expanding and it reaches infinity. My R is at infinity, the radius of that disk is infinity. So if you view it, it would look like an infinite plane. Alright, it would look like an infinite plane. And if I work on this, if I put my R as infinity in this particular, okay, so this ratio will reduce to 0 and my E will become sigma by 2 epsilon. Okay, and there are different ways to calculate the electric field of infinite tree, but this is one way where you can confirm that it's equal to sigma by 2 epsilon. Okay, so I have covered the first part of my electrostatics, all the formulas that I used as a JAM aspirant and that helped me crack the exam, and I hope it was helpful for you as in for a revision purpose. Now if you like this kind of a revision session, do let me know in the comments, and if you have any suggestions for me to improve, do let me know. And also do share this with your friends so that it can help them as well. So and overall, the reach or the purpose of this particular video is to help the aspirants in the last month with the revisions. So just share this with your friends, and if you want to have the further series of this particular electromagnetic theory, do let me know in comment. If the response is good, I will surely try to make more videos. Thank you.